This is the 10th video about the wind turbines. In the last video, we talked about the classic blade element momentum method, or BEM. In this video, we will discuss two highly important corrections to the classic BEM. One is called the Prandtl's tip loss factor, and the other is the Glauert correction for high values of the axial induction factor. If we look at the wings of an airplane, the pressure underneath the wing is higher than that above the wing. This pressure difference caused by the airfoils creates the lift that allows the airplane to overcome gravity. But also because of this pressure difference, at the tip of the wing, air tends to flow around the tip from lower to the upper surface, thereby reducing the lift near the tip. This flow is called tip loss. As the airplane moves forward, or the wind or the air actually moves in this direction, right? This flow around the wingtip creates a trailing vortex, which is essentially a weak mini tornado that can affect other objects that's passing through it. This phenomenon has been observed in wind tunnels, and it's kind of sketched in this particular graph. For wind turbines, because the blades have finite length, so tip loss also occurs near the tips of the blades of the wind turbine. Unlike airplanes that move along a straight path, the rotational motion of the blades creates vortex sheets of free vortices. Those free vortices are kind of oriented in a helical path, behind the rotor. The strong tip vortices are kind of located at the edge of the rotor wake, and then the root vortices mainly lie on a linear path along the axis of the rotor. And again, these vortices have been observed in both in wind tunnels, and also it's also sketched in this particular graph here. The classic BEM method has two components: the blade element method, the blade element theory, and also the momentum theory. Right? The conservation of linear momentum, which gives us the expression for the thrust force, is based on the actuator disk model. And the conservation of angular momentum, which gives us the expression for the torque, is based on the rotor disk model. Right? Both of them are based on some kind of disk model. So in a uniform disk, in both in both the actuator disk and also the rotor disk model, we are considering a uniform disk. Right? A uniform disk can be thought of as a rotor with an infinite number of blades. But in practice, the number of blades is always finite. So there's a discrepancy between our highly ideal abstract model and the reality. Right? In the abstract model, we are basically assuming an infinite number of blades, but in reality, we have a finite number of blades. So to account for this kind of a tip loss effect on turbines with a finite number of blades, Prandtl derived a correction factor F, to the equations of the thrust and torque. So all we need to do is to actually multiply this particular factor F on the thrust force obtained from the actuator disk model. So this equation was actually copied over from video 9. Right? This is actually when we are applying the momentum, when we are actually deriving the thrust force on a ring based on the actuator disk model, based on the linear momentum conservation law. Right? That was the thrust force that we derived in video 9 based on the actuator disk model. Right? And all we have to do is to actually multiply this thrust force with the factor that's called F, Later on, I will show you the expression for f, right? And everything else is kind of similar, right? And we for the angular momentum, we derived the torque. This is again a slide copied over from video 9. In that video, we talked about how we actually obtained this torque based on conservation of angular momentum, right? And this is based on the rotor disk model, again assuming a infinite number of blades. Right? So if we want to account for the effect of tip loss, then all we have to do is to multiply this dq with the same Prandtl factor f. And this factor f, which is called Prandtl tip loss factor, is defined in this particular way. D equals to 2 divided by pi, the inverse of the cosine. The inverse of the cosine function, basically a cosine. It's a cosine. And then the input to the a cosine function is the exponential function with the exponent given by minus f. And f is given by this particular expression. That's based upon the radius of the ring, right? The radius of the ring. And then the phi angle. The angle phi is the angle of the relative wind, right? We need to pay attention to the unit of f. The unit of f. For this particular formula, the unit is actually in radian. It's not in degrees, right? If we would like to obtain f in degree, right, then all we need to do is to actually replace this 2 over pi here with 1 over 90. If we replace 2 over pi with 1 over 90, then the output, the factor f, is going to be in degrees. The expression for the two induction vectors must now be updated now to account for this newly introduced factor f. So without the Prandtl's tip loss factor, the two induction vectors were looking like that. We derived those expressions in the previous video, right? But now, if we want to account for Prandtl's tip loss factor, then the actual induction factor has this kind of expression. Instead of a 4, you have a 4f here. Right? And then for angular induction vector, it's a 4f also, right? Instead of just a 4. And f is given by this particular expression. And this expression only depends upon radius and also phi, the angle phi. And phi can be computed, basically. Right? And in our last video, we gave an iterative algorithm for computing the two induction vectors. And at step 2, at this particular step, right, we computed the angle of the relative wind, phi. That's the tangent of phi, right? Once we know the tangent, we know the phi. So the Prandtl's tip loss factor can be computed right after the second step, after we have finished computing the angle phi. Right? Because the Prandtl's factor only depends upon phi. For a given ring with a certain radius, right, r is fixed. Capital R is the radius of the entire rotor disc, right? That's the radius of the tip of the blade, basically, right? So the calculation of the Prandtl factor can be inserted right after step 2 is finished, right? And then at step 5, we were computing the induction vectors using those two formulas, right? But now all we have to do is to modify those two formulas by accounting for f. That's computed after step 2, right? Using the f computed after step 2 to compute a and a prime, these two induction vectors, and everything else stays the same. And basically, that's the first correction that we were planning to talk about, because of the tip loss effect, right? We have to sort of account for that. That's probably one of the most important corrections that we need to make in order to make our theory more realistic, to make the BEM method more realistic, basically. And there is another correction that we must make. This correction is the correction that we must make when the axial induction factor becomes too large. The axial induction factor A could be quite large. in realistic calculations, it could be quite large. So when we were discussing the actuator disk model in the 5th video, we obtained an expression. We obtained an expression for the velocity of the wake, u4, right? In terms of the axial induction factor for the wind speed at position 4, right? That's u4, and u4 is at a position that is very far from the rotor, downwind. That's the wake speed. At that time, we did not consider the valid range for A, in which u4 obtained from this expression still makes sense, right? Suppose A is larger than 1/2, then maybe u4 becomes a negative, maybe it's pointing in the opposite direction, that kind of thing, right? Is it still valid, right? So A has a certain range for u4 to be still valid, right? Now suppose we increase the value of A gradually from 0. What will happen to u4, right? So u1 is sort of fixed. That's the incoming wind speed, the free stream wind speed, right? That's fixed, right? Suppose we increase A from 0 gradually. What's going to happen to u4, right? Of course, u4 is going to decrease, right? u4 is going to decrease. So at this point, A is not too large yet. So u4 decreased a little bit. So it's slightly less than u1, right? So this is the stream tube that we're actually considering, right? So out of this stream tube, it's still free stream wind speed. So those arrows have a speed of u1. That's unaffected by the turbine, right? But inside of the stream tube, the air is affected by turbine. So u4 is sort of slightly less than u1 now, right? Because the turbine has extracted some power out of it. So the kinetic energy of the wind has been sort of extracted somehow, by partially, right? So u4 must be smaller than u1. But because A is not too large yet, right? So u4 is just slightly less than u1. Right? Now we increase A a little bit, right? So now the difference between u4 and u1 has increased, right? So those vectors have a shorter length than the vectors that's outside of the tube, right? So the difference actually has increased. Now we increase A even further, right? So in this case, A is actually close to 2.5 now. So u4 is actually close to it's becoming very, very short, right? And the difference between u1, the outside of the wind speed outside the tube, and the wind speed inside the tube is becoming really big, right? So as the velocity difference between the surrounding free stream wind and the wake gradually increases, there will be some kind of a free shear layer at the edge of the wake, and this kind of free shear layer becomes unstable, and you'll get eddies. Some of the eddies will actually form behind, inside of the stream tube. Those eddies, when they are actually formed, they will transport momentum from the outer flow. They will transport the momentum from those outflow into the wake. And this particular situation is called the turbulent wake state. Right? So if the free shear zone becomes kind of the velocity difference becomes too large, right? Then you're gonna get sort of instabilities, and those instabilities are gonna create eddies, and those eddies are gonna transport momentum from outside of the stream tube to inside of the stream tube. And at this point, the actuator disk model actually breaks. The reason is because the actuator disk model is actually based upon this kind of a scenario, right? There's no momentum transfer in and out of the stream tube. So the stream tube itself is kind of a control volume, right? It's kind of isolated from outside. But now you have momentum transfer, and the wind is actually flowing inside of it. Right? flowing into the stream tube now. So it has broke the basic assumptions of the actuator disk model. Right. So in this kind of case, when A becomes too large, we need to account for this kind of situation. Right? And how do we actually do that? We can use empirical relations that was obtained from either labs or in real observations or in wind tunnels, that kind of thing. Right? Using empirical relations. But before we actually talk about the corrections for such high values of the axial induction factor A, let's introduce a new quantity called the thrust coefficient. In the last video, we obtained an expression for the normal force acting on the airfoil with the radius of r using the blade element theory. Right? That's a normal force. Right? We obtained the normal force by looking at the lift and drag forces, right, acting on the airfoil. Right. The normal force is just a superposition of the vertical projections of the lift force and the vertical projection of the drag force, right? And we obtained an expression for the normal force. Right? That looks like that. This is the slide copied over from the previous video, video 9. But we have added some more derivations here. Here we have used an expression for the relative wind speed, u real, which equals to u1, 1 subtract a divided by sine phi. Right? That's the relative wind speed. And this expression was also obtained from the previous video, actually. Right? So we bring this expression back into dFn, the expression for dFn. Right? Right? Like that. And we can sort of do some simplifications by replacing this very long expression with just one symbol, Cn. We defined the Cn in video 9, in the previous video. Cn basically just is a shorthand notation or shorthand representation of this kind of very long thing. Right? Basically, it's just that. So now we have an expression for the normal force acting on the ring. Right? And then what exactly is the thrust coefficient, right? Ct. Ct is the so-called thrust coefficient. Right? The thrust coefficient is actually the ratio between the normal force and this particular denominator. The denominator is actually 1/2 times density of the air. That's the free stream wind speed squared, and then the area on which this thing is actually acting on. So for the ring that we were considering, dA actually equals to 2 pi r times dr, right? And this representation of the area is actually on the first slide of the previous video, right? So all you have to do is to actually divide them. You can just divide them, and then after some simplification, you obtain this expression. Here we have used the solidity. It's a constant that we define in the. No, it's not a really constant. It depends upon the radius. Solidity is actually the ratio of. It's actually the fractional area that's covered by blades. So that's the solidity that we have defined in the previous video of it. So that's called the thrust coefficient. And we now have an expression for the thrust coefficient that we have obtained from the blade element theory. Right? We derived it from the blade element theory. And then the Glauert correction for high values of A gives you an expression also for the thrust coefficient. But it's not just one expression, it's actually two expressions. And depending upon the value of A, is it smaller than AC or larger than AC, you have to actually use a different formula. Right? So if A is smaller than AC, you can use this formula. But if A is larger than AC, you have to use this particular formula. And here, big F is the Prandtl's tip loss factor that we have talked about before. Right? And AC is about 0.2 basically. Right? So when A is smaller than or equal to 0.2, then you use this formula. If it's larger than 0.2, you use this formula. Right? And this equation is determined empirically. Right? This expression for CT, these two expressions for CT are determined empirically using either experiments or using the calculations. Right? And in order to actually apply this Glauert correction, this CT that's given by empirical relations must equal to this CT that we have derived from the blade element theory. Right? So this equality allows us to obtain another expression for A here. Right? So if A is smaller than or equal to AC, then this expression applies. And this expression is actually exactly identical to the equation that we have obtained by applying the Prandtl's correction to the actuator disk model. Right? This expression is exactly the same as this expression here. Right? So when A is smaller than the critical angle AC, this equation still applies. This expression for A still applies. When A is larger than the critical AC, right, then now we have a new expression. Right? And this very long expression actually depends upon a new value, new quantity, that's K. Right? K is defined on what? K is defined in terms of Prandtl's correction, Prandtl's tip loss correction, right? And sine phi, the angle of the relative wind, right? And then Cn is the Cn is this thing, right? Cn is this thing. Again, depends upon phi. Cl and Cd are something that we read from we can read from a table, right? So once we know phi, basically we can compute A, right? We can compute A. Now we have a modified iterative algorithm for computing the two induction vectors now. So this is actually the BEM with Prandtl's tip loss correction and then the Glauert's correction for high A values. Right. First step is still the same, initializing A and A prime. Most of the time we initialize to 0, right? And then the second step is still the same, compute the angle phi, angle of the relative wind, using the assumed A and A prime, assumed induction vectors. And then once we got the phi, we compute the Prandtl's factor F. Right. And then we still compute the angles of attack, read off CL and CD, the lift and the drag coefficients based upon the angle of attack alpha. And on the fifth step, we have to compute the induction factors using the new formulas. A prime is different from the A prime we obtained from the rotor disk model by the difference is just the one factor F, and this factor F was computed at this particular step. Right? And then the expression for A must be modified to account for the Glauert's correction for very high values of A. So when A larger than AC, you have to use this formula instead of this formula. Right? And then step 6 and step 7 are still the same. So that's the BEM with the two most important corrections.